Hi, I'm Bill Laboon, and I'm here to provide a short explanation of what Polkadot is and how it works. Polkadot consists of a central relay chain which coordinates parachains. These parachains are special purpose blockchains built for specific tasks. These parachains can be built with a framework called Substrate, allowing developers to easily pick and choose which features they want on their parachain. After the parachains are developed, they are connected to the relay chain, and all of these parachains that are connected to the relay chain can interoperate with each other. Since each of these parachains is specialized for certain tasks, such as social networking or decentralized finance or smart contract execution, they can perform much better for that individual task than a single general-purpose blockchain. Polkadot also includes some other features which allow it to grow and evolve. Some of these include on-chain governance, that is, allowing users of the network to vote on the future of the network, and forkless upgrades, that is, updating the rules of the chain without insisting that node operators download and install new software. Additionally, Polkadot does not require the massive amount of electricity that legacy blockchains require to mine new blocks.
All right. Hello, everyone. Seems like there's no one join this live stream yet. Um, but anyway, maybe like just start, and so who interested gonna can rewatch the video on YouTube. Okay, so today live stream topic. So we're gonna talk about like Merkle Tree in blockchain. So Merkle Tree is a very common data structure used in most of the blockchain right now. And some blockchain doesn't have Merkle Tree, but it also have a variant of the Merkle Tree. So, but maybe like first, before we go dive deeper into the implementation of the Merkle Tree in Rust, we're gonna talk about like what is the Merkle Tree. Let me see. So, if you're a computer science student or a computer scientist or a software engineer, you may know about Merkle Tree. You may know about binary tree data structure. So what is the binary tree data structure? So binary tree data structure, you're gonna have one node, and then like this one node gonna link to two other node, and then like one node is gonna link to a left node and a right node again, and then let's construct this tree like this tree like this. So for Merkle Tree, it's different. So let me go to the Merkle Tree. So as you can see right here, so this is the Merkle Tree. So Merkle Tree compared with the binary tree I already saw before in like in the traditional binary tree, it's similar, but what is the difference here? So the difference of the Merkle Tree is gonna have like multiple data blocks. So we call like the deepest layer of the Merkle Tree is a data block, and then like each data block is gonna become a hash, and then each hash is gonna construct to become another combined hash. So what's the purpose of this structure? And like why don't we just use binary tree instead of the Merkle tree? So maybe like you should watch the video right here that I already prepared, so like to understand fully what is a Merkle tree.
Merkle Trees. Merkle trees are used to store the data in a structured way. It allows for efficient and secure verification of content in a large body of data. Merkle Tree checks consistency continuously. It is easy to retrieve data through the Merkle Tree. A Merkle Tree produces a digital fingerprint of the entire set of transactions. It therefore enables a user to verify whether or not a transaction is included in a block. To know more, download the block.
Yeah, so as you can see, like it's quite simple. So Merkle Tree is produce a digital fingerprint. So every hash right here is a digital fingerprint in a tree data structure. But what is actually a digital fingerprint and why is it used in blockchain? So digital fingerprint is to provide you a verification ability over the data stored in the data structure. So for example, like if I got if I got transaction A and just transaction B, like to check if the transaction A in the blockchain, you just construct a Merkle tree and you got a top hash, and then like you provide the hash of the data, then you're gonna know like what if that data is in the tree. So in theory, like if we just present broadly like that, like it's quite hard to understand. But maybe like after I give you the implementation in Rust, you're gonna understand it fully. So yeah, so that's the Merkle tree. So about the application of the Merkle tree, we use Merkle tree in a lot of things. First is just short the Merkle tree in state machine. What does that mean is in the state machine, like what in the state machine, like I always give an article on the group about like a state machine. Like a state machine is basically a data structure that is have a state, which is a full database of the blockchain, and as transactions is like every operation on the blockchain that produce a state transitions on the full copy and DB of the database. And in that way, like you may know like if that transactions is valid. So to check like if the transaction is valid, the most optimal way is to use a data structure like Merkle tree. So that is one application. And then the another application is NFT whitelisting. Yeah. NFT whitelisting. So what the NFT whitelisting? So NFT whitelisting is basically like to whitelist someone to mint the NFT. You want to store something that is must be secure enough, and also that must be optimal enough, so that you can retrieve the verification later to check like if like that entity truly in the blockchain is duly registered as NFT whitelisted address. And then like for most of the NFT whitelisting, we also use Merkle tree. So you just search like NFT whitelisting solidity, and you're gonna see like there's many implementation for NFT whitelist app that allow you to whitelist Web2 address, whitelist public key as NFT whitelisted entity. Okay, so I think like that's much of the theory. And then if you got any questions, so just comment below. Maybe like, and right now I'm gonna go directly to the code so that you can gonna understand like what is a Merkle tree in a hands-on experience. So right here, like I already have the code, like the code template for the Merkle tree. So if you want to, and I also like repair this source code on the low leveler GitHub. So you just go to GitHub of the low leveler, then you visit what's up source code, and you're gonna see Merkle tree. So this Merkle tree, I already repaired the template for you. So that you can practice on your own to implement like all the to implement some of the most basic functionality of the Merkle tree. And then, so in today's tutorial, I'm gonna try to finish this implementation of the Merkle tree. And then I'm gonna push the code to the repository so that you can visit later. Right? So let's go to the code. So here's the code of the Merkle tree. Maybe let me give you a quick overview of how the code structure. So in the Merkle tree source folder, you're gonna have a hasher, a lib.rs, like a Merkle tree.rs, and the source 256.rs. So the hasher is a tree that it provide information like if any struct that is implement the hasher, it must follow, like it must provide some functionality over like hash, concat hash, and hash size and hash to string. So what does this method mean? So for hash, like this method receive a byte. This method receive a byte, and this convert this into a hash type. So this hash type is an associated type that you're gonna have to learn in Rust concept before. So basically, like anything that is implement the hasher trait, it must define this type hash, and this type hash is the type that is must, like the struct must implement on this trait to be a valid hash type. So this hash method, as I explained, like this method receive bytes and is produce a hash type. How about like concat hash? So concat hash is gonna receive, this method receive 2 bytes. I can say like two hash type, and then it's gonna produce 1 hash type because it's concast 2 hash together. So why do we need that method? So let's go back to the Merkle tree. As you see right here, like when you provide a data block, let me remove this. Yeah, so when you receive the data block, you want to hash the data block into a hash. So this is where you need the hash type, the hash method, as I mentioned. And then when you got 2 hash, you want to combine these 2 hash, or just like concatenate these 2 hash into 1 final hash. And this 1 final hash must be an output of that concat hash method. So let's go back to the code. So we already understand like what is it concat hash about. So about the implementation of the concat hash, we're gonna want to convert the hash into a vector. That's the reason why we have a trait into vect u8, and then like after we can convert this into a concatenated variable, we also like check if there's a right node. If there's a right node, then we concatenate 2 vector into 1, and then like we hash the whole big vector. And then if there's no right node, we just return the left node. So because like the Merkle tree, let me go to Merkle tree visualization so that you can understand it fully. So just imagine if we provide a tree with the number of hash is with the number of data block is 5, then you're gonna receive a tree like this. So in this tree, like you have 5 data block. So because it's a 5 data block, so it's gonna produce an odd number of leaf node. So this is called leaf node. So because you say like 2 data block is combined together and it's become 1 leaf node. 2 data block become 1 leaf node, but this one is cannot combine with anything. There's no right node at all, so it's just produce this 1 leaf node. Then like you got a root hash. We're gonna go to this to combine this root hash later. All right, so we already know about this concat and hash method. How about hash size? Hash size basically just return the size of the hash. And then hash to string is to convert the hash to string. Simple, right? Now go to the source 256. The SH256 is a cryptographic algorithm for hashing. So you can look at that later on Google. But basically, we're gonna produce we're gonna we're gonna implement the hasher straight for this source to physics algorithm, and then like you got a few methods like, and then you're gonna have to implement the method like hash and then hash to string. So for hash, we use the library called SHA to physics, and then we digest the data. Then we gonna produce we're gonna copy the whole byte into this line. And hash to string is basically to convert all the bytes to string to character and then concatenate them together, become a final result. So that's what SH to physics algorithm do. And I also have a few tests. So if you run the test right now, you're gonna see if like, oh, not this test. If you run the test for the Merkle tree right now, you're gonna see it's failed because like we don't have any method implement yet. So yeah, that's all for the structure of the source code. And now we go to like the detail of the Merkle tree. So for Merkle tree, we have a few methods like first root hex. I say like root hexadecimal, and then the second one is from leaf. What does from leaf means is like you provide I call a data block a leaf, and then like you provide a vector of leaf, and then like, it's gonna hash those leaf, and then concatenate them, and then like produce a root hex, and then it's gonna return a Merkle tree with of all the leaf. Then we have a verify. What a verify means is like you provide is a hash. So what should work is you provide is a hash, and it's going to return a boolean. That's mean like you provide is a hash, and it's gonna check like if this hash is in the Merkle tree. If it's in the Merkle tree, then it's provide boolean. Then you got like the print tree, just like in binary tree or other tree, the structure, you print the whole tree in multi-level, and then the depth is the depth of the tree. So now we're gonna implement this data structure. So maybe like first I'm gonna implement the from leaf because it's the most the foundational method for all the other method. So for the Merkle tree, I will call it data blocks, and then this data block it must receive the hash. It must be a vector of hash, and then you have I'm gonna call it level. This level, and then it's gonna be like multi-level of the hash. So now go to the from leaf. Maybe I should call it from data block, but yeah, anyway. So what we want is that we want to return this method, and then it's a phantom data. So if anyone don't know about this phantom data is basically phantom data is basically just the type to help the compiler to infer the type in the struct Merkle tree, because like we have a hasher right here, and we don't know like we don't have any field that implement this hasher type. So basically we just have phantom data. Actually like this do nothing. It just give information to the compiler. So just ignore it. So whenever like you want to have like a generic type in the struct, but you don't have any field to implement that type, then you just have a phantom data. And for data block, so data block is going to be the leaf, the reference, and then the level. So what does the level mean? So here like we have the most base level. What we want is going to be the leaf, and then like a second level of the leaf, which is the hash up on the data block. So let's go back. So as you can see right here, this is the data block, right? Like the green one, the green one is the data block, and then you want to produce the hash of of each data block. So it must be the upper level of the data block level. And then you got like the upper level, which only 2 nodes, and then like the, I can say like the deepest, or I can say like the most narrowest level is the root hex. It must have only 1 leaf node, which is the root. So let's go back to the code. So what we're gonna do, like we have to go to on the data block, right? Yeah, but right here, like we have to step by 2. So I can say, let's see why. We're gonna get the index, the pointer. I can say it's a pointer. And then we leave, get pointer again. So this method get is gonna produce an option. So an option, it can be none or as a value, right? As you can see, like the type is it's gonna be an option of the hash. So it's gonna be none or it's have to produce a value. And so right here we want to make sure like the left node is always there. Like we always have the left node. So maybe just unwrap because we confident that the left node is always there. And then we check like if the right node. Oh, actually you don't need to check the right node because like our method concat and hash is already handled that. So we're gonna have I'm gonna have call it concatenated hash. It's gonna be what is it? Concat and hash. As you can see, because like this our method like is receive an option. So we just pass in the get right node directly, and we don't care if it's gonna be none or have a value because like in our concat and hash we already handled that. And now we have like concatenated hash, but we also have to handle like our pointer must be plus by 2, like we step by 2. Right, because like we want to get like the left, let's go back, want to get like the left and then right, left and then right and then left. So we have to step by 2, and if there's no value for the right, it just become none, but we already handled that, so we don't worry. And we got like concatenated hash, so we got upper level. So our upper level is also become the vector of the hash. Our upper level is gonna receive the concatenated hash as the output. So this one, like we already handle the first level. We already handle this level right here, and now we want to we have to run a recursive code to handle like all the other layer. Upper level, don't leave. So we can call a method called like put view level helper, and this view level helper is gonna produce a vector hash. So we have to check, maybe just convert this to y. So y, the pointer, larger than the leaf dot length minus 1. Just larger or equal. Yeah, it must be larger than. Then you got like upper level. But the upper level has to be like this. And then you got view level helper. Merkle Tree. And then you self. Let me just call self. From leaf again. So we have a recursion here. So from leaf, and then like what kind of leaf is this? So we're gonna provide the upper level into this method. Oh, this must be new level helper. Oh, because view level helper is also return the vector. So I think it should return here. And then this one return the upper level only. It's only return the upper level. And then you from leaf, you're gonna have level. View upper level. Leaf. Oh, let me see. How can I make a recursion for this one? So we want a method, maybe just make a lambda. View level inner. Then we got a lambda. So this one is going to receive the leaf as well. That's mean like we provide a list of data block, and then we return this, upper level. So let's go to this, and then order. See, the upper level. So it's gonna be the leaf, and we build the upper level of the leaf. The level inner block. Yes. Yeah, so like we already implement that. We finished the method. I don't know whether it's gonna be correct, but let me try. Then you got the level is view level helper. So we receive the leaf, and we will receive the level. Provide the level. Actually, we don't need data block because we already have the level, so just ignore it. You can still have that field data blocks as like a proof of your original input or something, but we can ignore that. That's fine. So after we already have the level, we can print the depth of it. So just basically do level, and then like level length -1 print tree. You go to now to print the tree, to print each level of the tree, we just go to per each level, and then we print the level, right? So we have level of level in level, and then right here you're gonna print the level. We want to enumerate, so the level index. Oh, you missed the debug tools. See, we have to add debug right here if we want to print it out. Okay, so now we already finished most of the method like print tree, depth, and also from leaf and the build level helper. So we also now we run the test a bit to see like if it's correct already. Run the test. Seems like it's failed. Oh, because like we never build the root hex. Easy. So as you see, like go back to the visualization. So we have the data block. We build the upper level and also like the upper level. And now like our top level is gonna contain the root hex. So we just return like the last vector in our list of vector. So here we already have a vector of levels, and then you just return the root hex from it. Style level, last, and wrap directly, because we already know that it must have a value. If it doesn't have a value, then it's not a correct Merkle tree, so that's fine. Then like we last again, then we unwrap. Oh, actually, like you don't need to unwrap because we must return an option. String. Okay. Let's return a string. Where's the hash? OTD is the hash already. Let's do string. Now we have a chance to use our method hash to string to convert this to a string. So we must do match sum then hash. Oh, actually, you can do hash. Expected option string for string, that's fine. None. All right. All right, seems like we have a bug here. That our left, no, it just return a none instead of a correct hash. So what should we do? Like we just because we have a method to print tree, so we just print it out. Oh, I should have print it in the string instead of the whole text. So each level is a vector, right? So we go for so you can see right here, we receive a correct hash for the first layer. So we have a correct hash for the first layer, but seems like it doesn't concatenate in the right way. So we're gonna have to change it a bit. Each level index. Go back. Okay, let me turn on something. All right, so our base layer, that's a block layer. We have all the hash. Now let's go to the method from leaf. So from leaf, as right here, view level helper. Then we provide the data block. In the data block, we see, so now like we can combine and we will use the hash in it. So you can see like we got like we1 oh, so like we missed the topmost layer. We missed the topmost layer. New layer level here, leaf, layer key, that's a block layer. No, I think it should be the leaf as well. That's a block layer. I'll just say like her leaf in your layer. Oh, right here it doesn't produce any recursion. That's my mistake. Just build the upper level. This doesn't take the next step on the recursion. So that's the bad thing. So we have to handle the recursion here. We want to handle the recursion. First, we must produce the layer. So it's really a layer. Layer. And then we sound Like right here, we have to concatenate the vector. We have to concatenate. Oh, see. Still a bit weird. Ah, finally. Let's put the test. Oh, no shit. Oh, I forgot I didn't have recursion. So, return. Base for this recursion algorithm, like go to 0, it could be 1. So we just right. Really? So let's return. Interesting. I don't know if whether it's gonna be the test, right? But at this point we can already feed the whole the whole tree right here, right? So we successfully in our first step. Now we just go back to the test and then we see like if our path is the right way, is the right thing. Yeah, right here just reference from other open source code to get the test. We have like all these tests. And also we have like this value on those. Let me just convert on the test to Rust so like we can test on those, because I like that that's open source Merkle Tree and already tested before, so I know like all the test case is right. But for this one, like I'm doubt that it's not the right one. I just basically copy on the test case over so that we can test. This one is must be. So. Wait, what? Allocation are not allowing. Okay. Move boundaries. I think for test case good enough. All right. Then let's wait, what? Never see something like this. Wait, it must be. It's missing something. All right. Sorry, this might be time consuming a bit. I have to set up the test again. Okay, let's go test again. See, it's already correct. Awesome. And now we're gonna test all the test cases. We just loop all the test cases. Test cases, and then have the test data. Maybe just call it test data. Select it. Come on, what did I say? Oh, it's a vector of nothing. Oh, we have to convert that. So we have a string. We have a string that we want to convert hash. We're gonna hash all these values. It's by hashes. Okay. Use that. Oh, we have to collect. Expected text. Now we run the test. Let's see the magic. Shit. What the hell with that? Seems like the row is incorrect. This can be. I think this can be because of this conditions. The text here. Let's copy this over. Yeah, the setup should receive the indexing. So no, what's wrong? Oh, so it seems like the first test case already correct. Just like so the rest is bring the divider here. I don't know the root set, is it? So it's failed at the second test. It's failed at the second test. It's our second test. Yeah, because like we didn't copy the input. So that reason why. That's the way of it. Yeah, you see, like expect the root head is duplicated. Use copy. Awesome. See, on test passes. That means like our method to build the root hack is already correct. Now we only have one method left, which is verify. See, okay. So for this verify, what does this mean? What does that mean is like, let's go back to the tree. So in the verify, for example, like if you provide this if you provide this hash, and then I have a root hex. I want to, I want to validate if that root hex is in the Merkle tree. So that's the purpose of that verify. To do that, here's what we do. Let me see. Merkle tree verify here. So like for the Merkle tree, you only need two hash. First is the root hex, and the second one is the one that you provide to the verify method to know like if that root hex, if that hash is in the Merkle tree. So the green block right here is the one that we provide to the verify method, and this is our root hex, right? We already calculate the root hex, and then we can provide like any kind of data block hash to the Merkle tree verify method. And to verify, the algorithm works by like you got the neighbor node, you got the neighbor node of the hash, and then you combine them together to become this block, and then you also got the neighbor node of this hash and combine them together to get another the node until like you got another root hex. Then you combine that root hex with a new one. If those two is the correct one, then you already have a correct Merkle tree hash. So that's verify method gonna return true. So let's go back. Okay, so now to verify, when you provide a hash, we want it to return a neighbor. So we maybe gonna have a method called like find neighbor, and this find neighbor you have now, and then hash. So this find neighbor must return another hash, or it can be an option maybe. Okay, so to do that, we start from the base layer. If the base layer doesn't have any hash, then we go up. So to do that, we have C level. Then like this level is like and then we just loop through the level, or maybe we can do like find. Oh no, identity method to shut or element in the vector. I don't remember. Maybe I just do iteration. The node in level. So if the leaf node equal to the hash, that means the hash is in this level. And now we need to know the index of the leaf node index. So we call it leaf node index. So if the leaf node index equal to 0, no, it should be if the leaf node index equal to 2. No, like it's divided to it's more division. I don't remember like how you say it in like it's if it is an even number, that's mean like it's become like this. It's an even number. For example, you got like A, B, C, maybe like 1, 2, 3, 4, 5, 6, 7. Now if it's an even number, which means that it starts here, that means like it's a leaf node. Right? So it must take the right node. Yeah, now it's a left node. Then this must take a right node. Then you got the right node. Just keep it none. Else the left node. Then you go yeah. Then you delete index +1. This must be that. Index. So for find neighbor, I think like we need to return the hash and also like the parent one. So it should be the hash, the option. Return. Okay. So the hash left and get right now. Then we got get right now. This must be correct. Oh, it must take two values. Oh, actually, why do that? So if there's a left node. Wait, but there must be a left node. It sounds so weird. There's only a left node. Only left. Get. You can hash up the left node with the right one, and then we get the right node. Get left node and right. We match that node. Left node -1. It's here -1 here. So it must be on way. It must on way enough that value. Let's mean here. Check the left one. Just check the left. All right. Finish my neighbor method. I don't know whether it's gonna right or wrong, but let's try it. So verify your robotic hash and the level define the neighbor. So the verify method must be another recursion. So maybe that we're gonna need find label helper or something. So let's go to all the label on all the level in cell level. Then we got cell find neighbor. We got hash. I find neighbors. So level. Oh, it must be wrong. It must be another level. Go up to another level. If it is none, that's fine. Continue. So if the neighbor has, there's no neighbor has, we continue. Otherwise, if that, if not level, if not equal to hash, if it's not equal to hash, then it's none. So if gap in fact is none, we return false. Otherwise, we have oh, actually maybe I want another method called path. Oh, all right. Finally. Yeah, so we finished the implementation of the method. I hope that you guys understand it. But basically, like we try. I have a method called like five path to root. So what does five path to root mean? It means like we have a tree right here, and then as I explained, we're gonna want to get all the path up to the root. So it's gonna be a vector of the hash to contain on a hash lead to the root, and then after you got the path, you will check like the latest the latest element in the vector. If it is equal to the root hex, that's mean like our provided hash is the right one. It is in the Merkle tree. This one is must actually right. Do that. We don't have any test case for roof, is it? Roof. Maybe we just try it right here. Or we do tree. Five path to root. So let's check the path. Setup. Test data. Hashes. So, so we got the path, but it's only have one element. Hilarious. What a B. This B. Wait. B. With B. The element right here. Oh, we're missing something. So for the path, what is push? Must push. Because we find the path, we must detach in the neighbor. Not the detach neighbor hash, but we the get neighbor hash. The D1, yeah, it's correct. So we found this one. Now we just have to go up a bit. So after you got like the get neighbor hash. After you got like the get neighbor hash, it's gonna have to go to another level. But this one, we have to like current hash equal to hash. So and then current hash. It's correct. It's the current hash must be the get concatenated hash. See, you got on the path here. That's awesome. It's really awesome. So first is the D1, correct? Then these two combine together, it's become the B3. Yeah, it should become the B3. So like, oh yeah, because it's become a B3. Then B3, you're gonna have to find the element of the. So after you get the B3, you will receive the neighbor of the B3, and then this B3, and now like the concatenated hash of these two is combined together. It's gonna be like the 5.0, then you got like the F77F7, then you got like the final one. So now that you got like HL, HIJ, HMOP, but I think that we want to store the root too. So let me see. We need to store the root, right? I think like the last one is store the root. Yeah, that one's store the root. Oh, I think that we received a few comments here. Live này mình có record lại cho nên là có gì mấy bạn xem lại YouTube cũng được nha. I think like we're nearly done all this algorithm. But yeah, I think like now we need to just push the get concatenated hash final one, and then we are good. So our current hash, we can get neighbor one. Current hash. So we check like if the level is the final level, then we also want to push our concatenated hash. No, it should be one. Then we push the concatenated hash, get concatenated hash, and that. Right. So, interesting. Why there's an issue returning the level points to 1? What the heck? What's all four? A4 2 West 1. Oh, I think that's this. All right, we are on the path successfully. All right, everyone. We already finished the implementation of the Merkle tree. All of our tests is returned true right now. Like even the verify method is returned a full path. So yeah, so that's all. That's all from today's live stream for the Merkle tree. And thank you for for following me in the past 1 hour and 30 minutes. And it's a very long session, but I hope you guys learned something from it. And sorry if the quality is not that great, and I will try to improve it better in later sections. And hope you guys like it, and please support the low levelers in the later sections. And see you guys in the next stream.